This is an introduction to assembly programming using RISC-V. We will cover all the topics listed here. The only prerequisite for understanding this video is to be familiar with how numbers can be represented in binary, decimal, and hexadecimal. Let's begin by writing the simplest possible program. This program is going to contain a single instruction, which is the eBreak instruction. If we try running our program, we'll see that this error message appears. We do not yet have the background understanding necessary to understand precisely what this error message is telling us. That will be covered in a much later video. For now, what we need to understand is that the CPU, when it runs our program here, is not going to automatically know where the beginning of our program is unless we explicitly tell it. And we can do that by using these two lines right here at the top of our program. Now when we run our program, we see that our error message disappears and our program runs successfully. When we ran our program, it executed the eBreak instruction, which caused it to immediately stop. Let's make our program more interesting by adding another instruction. The next instruction we're going to learn is called the add immediate instruction. The add immediate instruction is going to take three operands, which are like three arguments that tell the add immediate instruction kind of in more detail exactly what it's supposed to do. The way that the add immediate instruction works is that it's going to take whatever value is stored in the A0 register. And so to explain what registers are real quick, over here we have a view which shows us all of the registers that are inside of the CPU of our computer. Now the CPU needs to be able to actually store the data that it's currently operating on, and registers are that place where that data gets stored. And so each register has a name, which we see in the left column right here, as well as whatever the value is currently stored inside of that register. And so we can see at the moment, almost all of our registers just have a value of 0 inside of them. Now what the add immediate instruction is going to do is it's going to take whatever value is currently inside of the A0 register. It's going to add the immediate value, which is the number right here, to it. In our case, there's currently a 0 in the A0 register, and this is a 5, so 0 plus 5 is going to give us a total of 5. And that result is going to get stored into our destination register, which is the first one right here, which is also A0. And so if we run our program, we see that we end up getting a 5 stored inside of the A0 register. Now we can create a copy of this instruction. We can write into another register, so we can put the value 15, for example, in here. So now when we run our program, we'll see that two changes occur. One is that we do the addition like we did before, where we add the 0 that's in A0 plus 5, and store it into the A0, so we get our 5 right here. And then we repeat that process again, but this time with the A2 register and the value 15. And so we get this 15 right here. If we want, we can kind of chain these together to do a little bit more of a complex computation. I can switch this A2 right here with the A0. And so now what's going to happen is we'll end up with the number 20 down here. And so when this program runs, it's going to start out by reading the value that's in the A0 register, which is 0 to begin with. It's going to add 5 to it and store the result in the A0 register. And so that's where we get this 5 right down here. Then, when we execute our next instruction, it's going to add whatever value is currently in A0, which now is 5 because we changed it after the first instruction. It's going to add 15 to it, and that's going to give us a total of 20. And we're going to put that into the A2 register. So we get our 20 right here. And then finally, we do our eBreak, which causes our program to stop. We can think of these registers over here as being this storage location where we can store kind of the intermediate results of all the computations that we're performing. And we can chain a bunch of these instructions together to do kind of more complex calculations. But a natural question that we might have here is, well, where does our code actually live? And there's two different ways that we could potentially answer this question. One is we can take a look at the motherboard and point out physically where it's located And 2 is we can give a logical explanation of where our code is located. So let's take a look at the motherboard first to have a physical answer to that question. So here's the motherboard of the computer that we're currently working with. Here we can see that we have our CPU core. All of these registers are located inside of the CPU core. And there's also a bunch of extra circuitry inside of the CPU that makes it possible for us to actually do the computations, do the calculations as we're running our program. Now, as far as where our code is, the code that we're running so far is located on this chip down here, which is called our read-only memory. Eventually, we're going to talk about RAM later on, which is this memory over here, which provides a lot more space. But for now, with the programs that we're running, all the code is going to be located down here on this ROM chip. And so that's the physical answer to the question, where is our code located? It's located on this chip right here. Now for the logical answer to that question, our code is located someplace that we call memory. In memory, we could think of as being this abstract, logical, mental model that both we as programmers and the CPU uses to organize the majority of the information that is being used by programs that it's interacting with. In this view here, on the column that we see on the left side right here, we're seeing addresses written in hexadecimal of the start of different sections. And so we can see 3 different sections right here. There's a large hidden section up here that has a total of 2.8 gigabytes of memory in it. We have a large hidden section down here that has another 1.2 gigabytes of memory in it that we're not kind of using for anything. And then we have this .text firmware section, which is where our code is actually located. It's only 12 bytes of memory, so it's very small. If we zoom in on it, we can see that we have now 3 different addresses right here that kind of line up with these rows here, where we see each of the 3 instructions from the program that we wrote over here. So when you write a program, every instruction that you write over here gets converted into a sequence of bits that represent what that instruction is. And that sequence of bits is represented in this column right here. So the actual information which is in the memory of our computer is located right here. And if we click on one of these, we can see the individual bits that represent a particular instruction. In this case, this is the add immediate instruction. And the way that the computer knows that this is an add immediate instruction is by looking at the bits that are in these 2 blue regions right here. If I were to click on one of these bits, it's going to have a new sequence right here, and we'll see that, oh, this is an invalid opcode, meaning that this is an invalid sequence of bits, so this isn't actually a real instruction that we can execute. So let's try changing a different bit here instead, maybe this one. We see that now we have a different sequence, and so we have a different instruction here. So this is now an add instruction, which we're going to learn about in a little bit. And if we flip this back, again, it's the add immediate instruction. So the bits that are in these light blue regions tell the CPU what sort of instruction this is. In the purple regions here, we see some more bits that say what are the registers that this particular instruction is going to operate on. So at the moment, we see this 01010, and that sequence of bits represents the A0 register. And if we flip this bit right here, now we have the sequence of bits that represents the A1 register. Every register that we see over here, except for the PC register, which is special, all of these have some sort of bit sequence that can be represented here to use with the add immediate instruction. In this orange region right here, we have some more bits which represent whatever the immediate value is. So you can see right here in binary that we have 101, which is 5 in binary. If we take a look at this next instruction, we can see that we have A2 right here instead of the A0, like the previous instruction had. So that was one difference. And then we see that we have these bits set right here representing 15. And so that's how we know what that instruction is. When the CPU runs, what it's going to do is it's going to start at whatever our start address is, and it's going to start running instructions one after the next all the way through until it gets to the end. So let's go ahead and restart our program here. And you'll notice that we have this arrow called PC, which is pointing to the first address in our program. We also see that over here, PC, and inside of that register, we see this hex B0000000, which is this first address, which is the start of our program. So PC stands for program counter, and this is a special register which always points to whichever instruction the CPU is about to execute next. Since we just restarted this program but haven't run it yet, it's pointing to the very first instruction. Everything else is set to 0. Now let's go ahead and step through the first instruction. So I clicked on step. You'll notice that the PC has now gone forward to the next instruction. PC over here has gone up by 4 to let us know that as well. And we see down here that we have a 5 that's been placed into the A0 register. What the CPU did there is it just read the instruction that was coming next. It took a look at all of the bits that are in these blue regions right here to figure out what instruction is this. Then it looked at the bits that were in the purple regions and in the orange right here to figure out what the registers and the immediate value or the constant was that it was working with. And then it executed that instruction and stored its results in our destination register. RD stands for register destination. RS1 stands for register source 1. In some instructions, we'll see that there's actually 2 sources. I think we saw that with the add. Here it is. So here we see that the add instruction, instead of having immediate value be the third argument right here, the third operand, we have 2 registers. So the add instruction will add whatever's in A0 to whatever's inside of it T0 and store the result in A0. So we have 2 register values that we're adding together instead of a register value and a constant. And so that's the difference between those 2 instructions. So we just executed our one instruction here. And next up we have another instruction, so we're going to step again. Now we executed that instruction, which did the 5 plus the 15 to give us 20, and it stored the result in A2. And so we see 20 over here stored in the A2 register. And now we're on the E-break instruction. And so when we step through that, we see that our program has stopped. So it says pause down here, and we're at the end of our program. Now you might be wondering here, we're at the end of our program, but what if we decided to tell it to step again while the next instruction that we're supposed to execute is this whatever comes next after the end of our program? We have this address here, B followed by zeros with a C at the end. So that's whatever address comes next right here. If we want to see what's down here, we can change the view to show unused ROM. And the camera just zoomed out a lot, and so we're going to zoom back in. We see here that in this region down here, we just have a whole bunch of zeros. If we want to execute the next instruction right here, we're going to go ahead and just tell it to step again. And you see that we get this error message that popped up. I'm going to drag this so we can see both at the same time here. So we see attempted to execute an invalid instruction, unrecognized opcode, bunch of zeros. So what happened here is the CPU took a look at the next instruction and it saw that there was just a bunch of zeros right here. We had an invalid opcode, so we got an illegal instruction, and so the computer had to crash in that situation. That's how we got this error message up here. Sometimes if you forget to write the E-break at the end of your program, you end up getting a crash like this saying invalid instruction, unrecognized opcode with 7 zeros right here for the 7 bits that represent the opcode value. Now you notice that this section right here is called unused ROM. So ROM here again stands for read-only memory, and that is referring to this chip right here. So this region of space, starting at address, this address right here, the B followed by all these zeros, going down all the way to this address right here, that whole region of memory is all supported by the ROM chip right here. Most of it's just zeros because we're not using it for anything. And just the first 12 bytes right here at the top is where we're actually storing our program. We just covered a lot of information, so let's work through a simple example that will help reinforce the concepts that we've talked about so far. Let's suppose that we want to write a program which is going to place the multiples of 3 into the T registers down here. So we're going to put a 3 into the T0 register, 6 into T1, 9 into T2, and so on. We can start by putting 3 into the T0 register, and we can do that just with an add immediate instruction, like we saw before. Now when we run this program, we see that we get a 3 right here. So we read whatever the initial value was in T0, which was 0. We add 3 to it, so we get 0 plus 3 gives us a total of 3, and we store that result into T0, and so we get a 3 down here after that instruction executes. We can then repeat that process with the T1 register to put the 6 value into that register instead. When we run it, we get the 3, the 6, and then our program ends. We could repeat that now 5 more times. And now when we run this program, we see that as each of these get executed, we get all of our multiples of 3 stored into our T registers. One thing to note when we run this program, let's go ahead and run it one step at a time again. Now, if you remember, so I accidentally clicked the step button here and we get this invalid instruction. That's because I tried executing whatever instruction just came after the end of the E break, which was all zeros. And so that's why I got that error. So let's go ahead and restart. Now we're going to step. You'll notice that every time we step, we're just going down to the next instruction. And also the PC register, the address that we have stored in here is going to go up by 4 every time, just like we see the addresses here going up by 4 every time. So a natural question here is, why are these addresses going up by 4 every time that we execute another instruction? And the reason is, each of these instructions here, it takes 32 bits in order to store that instruction. So we have 32 bits right here. There's 8 bits in a byte, so this is a total of 4 bytes necessary to represent an instruction. Every one of these rows right here contains 4 bytes of information. So there's 4 bytes for each one of our instructions, and so our addresses are going to increase by 4 every time we go to the next row right here to see our next instruction. The third instruction that we're going to learn is the add instruction. The only difference between the add instruction and the add immediate instruction is that in the third position here, we have a register instead of a constant or immediate value. Let's go ahead and throw those away, and we're going to use an add instruction here to set the value of T1. And since our goal is to put a 6 into T1, we could accomplish that by adding 3 plus 3. And since the T0 register has a 3 in it, we can just add the value of the T register to itself by writing T0, T0 right here. We can run our program again, and we see we end up with a 6 right here. For T2 here, we want to put a 9. And so if we want to accomplish that task of putting a 9 into T2, we need to add 6 plus 3. And since we have those available in the T0 and T1 registers, we can just write T0 and T1. So it'll add whatever value is currently in T0 plus whatever value is currently in T1. So that gives us the 3 plus 6. The result is 9, and it's going to put that into the T2 register. We run that, and we see we get a 9 right here. And again, we can do this for the next register up. If we want to get the 12 and put that into the T3 register, we want to add whatever's in. To get 12, we can do T0 has a 3, T2 has a 9, and since 3 plus 9 is 12, we can do T0 plus T2. This can become 2. If we run it, we get 12 right here. And again, we can just keep doing that same sort of thing going up. So for T4, we can do T0 plus T3, and that'll give us 15. And so we see the 15 right here, and we can keep going for the rest of these. Now, addition isn't the only operation that we want to be able to do. Let's suppose we want to do the following calculation. We want to figure out what 400 minus, let's do 400 divided by 2 plus 10 times 20. And so this expression right here is currently all green because we have this symbol sitting out in front of it, which causes a comment to occur. So if I delete this, you can see that it's no longer pure green and we get a bunch of these error messages. What a comment is a bit of extra text that you can add to a program that doesn't actually affect the program at all. And so oftentimes you can write a comment to say things like, this is the start of the program. And it allows you as a programmer to add like extra information, whether it's in English or just some equation that you want to write out. It allows you to add that to the program so you can read that, but it doesn't actually affect the code that gets loaded up over here. So you see that if we run this right now, all we see in our program is the add immediate and the e break, because those are the only two instructions that we have right here. These just get ignored. Going back now to writing more complex arithmetic expressions, we have this equation right here, or expression, which is calculating 400 divided by 2, which would be 200, and we want to add 200 to that, so it should give us 400 as our final result here. In order to do this calculation, we can approach this by first loading all 4 of these values into different registers. I'm going to start by putting 400 into the T0 register, and in the T1 register, we can load up a 2, and in the T2 register, we can put 10, and in T3, we can put 20. Let's run this program just to make sure it's all good. So we get 400, 2, 10, and 20. All that we have learned how to do so far is addition, but we have some other operators that allow us to do other types of arithmetic. So we learned add already, does addition, but there's also sub, which does subtraction. There is mul, which does multiplication. There is div, which does division. And there is rem, which will give you the remainder. And all of these operations work the same way that addition does. So let's change the operation to make this subtraction instead. If we want to calculate 400 minus 2, then we can just come down here and we're going to do the sub instruction. And we'll figure out where we want to put our result in a moment. But we want to subtract 400 from 2, and those are located in the T0 and T1 registers. So we're going to write T0 and T1. And let's put our result in, let's say, A0. So if we run our program, we can see we get 398 showing up here in A0. And it's because when the sub instruction ran, we took the 400 that's in T0 minus the 2 that's in T1. That gives us 398, and we store that into A0. We can now do the next part of evaluating this expression, which is to multiply 10 times 20. And so we can use the mul instruction for that. And let's put our result in A1. And our values are going to be in T2 and T3. So we could run our program again, and we see we end up getting 200 because of our 10 times 20 gives us 200, and we have that here. Lastly, we have this addition right here, which is going to add our final results. And our final results are going to be whatever the result of our difference was here and our product was here. So those are the values of A0 and A1. And let's put our final result in A2. So A2 is going to store the results of adding A0 and A1, So we can run that and we see we get 598 as being our total if we were to evaluate this entire expression right here. What the arithmetic instructions allow us to do is they allow us to perform any sort of arithmetic that we want, and we can chain them together in order to do more complex calculations than we otherwise would be able to do. Now, a natural question here is, if there's an add immediate version of the add instruction, is there also an add immediate version of the other 4 instructions that we have here? And the answer is no. Anytime that we want to subtract, multiply, divide, or do remainder by a specific number, then we will need to put that number into some register, like we did up here, and then we can use any of these 4 instructions right here on whatever that number is. Now, one kind of caveat to that is that the add immediate instruction is allowed to have negatives. I can put a negative, do a negative right here. So we're going to do add immediate with a negative 400, and we run this. We see that it puts a negative 400 here into t0, and then that'll affect all the other parts of the calculation later on. In all the programs that we've written so far, we have been quietly making an unsafe assumption. And that assumption is that the initial value in all of our registers here is 0. And we've been using that assumption whenever we've used the add immediate instruction in order to set a particular register to a particular value. Because we're assuming that the original value was 0 here, so we get the 0 plus 400 gives us 400. But it might not be the case that the original value in t0 was actually 0. And as we will see as we get into writing more complex programs, for the most part, we're never able to safely make that assumption. And so we need some other way of having a register right here in this location that is guaranteed to always contain the value 0. The 0 register right here does exactly that for us. So we replace the t0 here with 0, and if we run this, we see we still get the exact same result that we were looking for before with the 400 right here. Now, a difference that we're going to notice at the moment is that if we look over here, we'll see that it doesn't actually say add immediate like it did before. Instead, we see this li instruction, and we see t0 and 400. If we click on it, we notice that it's letting us know that li is a pseudo-instruction, meaning it's a fake instruction that is just a representation of some other instruction. In this case, it's the add immediate instruction, which is the original instruction that we wrote up here. And so if you look at the pattern of bits right here, you'll notice that it's the exact same pattern of bits that you saw in every other add immediate instruction that we've worked with. But the reason for this pseudo instruction existing is because it makes it much easier and simpler to write something which is very common for us to do in writing assembly programs, which is sometimes we just want to load a particular value into a particular register. And so we can just say load immediate, give the register name, give the number, and the instruction does what it needs to do, because it automatically gets rewritten using an add immediate instruction, and those are the bits that get put into memory. And so what the CPU sees is this add immediate instruction right here. Now there's another pseudo instruction, which is called move. MV is the way that we write that instruction, and then we give it 2 registers. The first register is the destination. So let's say our destination is going to be T1, and then the other register is going to be our source. So let's say our source is T0. So what this will do is it'll move whatever value is currently in T0 and copy it into T1. So if we run our program, we see that both of these registers right here have the value 400 now. If we take a look at what's happening here, we can notice that it also gets identified as being a pseudo instruction. The real instruction is add immediate once again. Instead of using the 0 register right here, we're using the 0 constant right here, or 0 immediate value right here. So when this instruction executes, we're taking whatever value is currently in T0, we're adding 0 to it, which doesn't change it, and then we put the result into T1. So effectively, we're just copying whatever's in T0 and moving it into T1. And so because this is something that we very commonly do, the pseudo instruction move was created to allow us to write this, which is a little bit shorter for us to use. If you would like hands-on experience with all the concepts that we've talked about today, you can create an account at visualemulator.com, then open the course catalog, go to Assembly Basics, Basics. Here we have a bunch of lessons and exercises that cover all the material that we talked about today during this video. Each one has a auto-graded component that helps test to see whether or not you've mastered the material. I'll see you in the next video.